All right. So this meeting is recorded, that we can also later post it on YouTube, similar to the one we had with Engine I before. But yeah, so welcome to this ceremony for the competition that was hosted by Novacene, was called Malicious Login Detection. Beck will soon say a few more words about Novacene and this one and the competition specifics. Just quickly introducing myself again and Aqora. So I'm the co-founder and CEO of Aqora. With Aqora, we are building this global community, quantum community platform that's currently centered around the concept of hackathons and competitions. Competitions like the one that we have the ceremony of today. The idea is to drive progress and also provide this platform where quantum computing experts like Peter and Oleksii, whom we will have both here today, can build up their portfolios and showcase their skills and how it applies to real world applications. And now, Beck, I'm happy to hand it over to you, saying a few words about Novacene and yourself.
Mhm.
I think first yourself, and then I will actually have a slide about Aqora, I guess. Sorry.
That's okay. Um, it's very lovely to finally meet the winners of this competition. Nice to meet you, Alexi and Peter, and congratulations. My name is Beck Langstone, and I'm the AI Solutions Analyst at NovaceneAI. We're based out of Ottawa, Ontario, Canada. And we run an intelligent automation platform where we take large amounts of data and turn them into insights. And so one of our use cases is cybersecurity automation, where we help companies build custom algorithms to do classification tasks. Um, yeah, we also do lots of text analytics, and we support a lot of different use cases with our platform. But
Right. Let me maybe then first jump again back to Aqora, and sorry, Beck, I think there will be one specific on Novacene. But yeah, glad to have you here. So just these few words again about Aqora. As I was mentioning before, we're building this platform. We actually do this now since basically for 1 year. Since then, we have more than 900 registered users. We're anticipating the 1,000 users. These users combined have submitted more than 340 quantum solutions now to these different competitions that we are hosting. And that's actually more than 38 use cases that we have addressed in this way by now. Right. Back to you.
so a little bit more about Novacine AI. So we're an AI-focused software engineering company, and we were founded in 2020. And we provide AI-based solutions to different types of companies, private and public sector. We have our flagship platform where most of our work takes place, where we use a combination of traditional natural language processing, large language models, and interactive data visualization to help people understand their data. Um, yeah, we are a team of software engineers, data scientists, and data analysts, and we all work together to make different solutions for the problems that our clients have. So we work across a variety of sectors. So in this case, where you guys have worked on the malicious login detection problem, that's our cybersecurity use case where we help our users take the information they have about um, classified threats or suspicious activity, build models, and also continuously improve them by providing feedback into those models and retraining them and redeploying them. Um, we also help work with law enforcement for decryption services. We've worked on search algorithms, mining, data preparation, and market research and sales insights. We help a lot of people understand survey data and text, as well as employee satisfaction. And we also do work with the Toronto Metropolitan University School of Journalism on named entity recognition and co-reference resolution to try and identify the voices that are being centered in media. But our challenge for you folks was to develop a quantum-based model to identify suspicious login attempts based on the Beth data set, which is a wonderful open source data set from a honeypot experiment. Um, and so this is to see if we can surpass and change the way we do things in terms of classification tasks. And
Yeah.
thank you so much, both of you, for your interest and dedication to making these solutions. It was really cool to see, like, especially on the very last day of the competition, both of you neck and neck, submitting different solutions. That was very, very cool. So thank you so much for your enthusiasm, for your participation, and for your really, really cool work. I'm excited to hear more about it. And congratulations again.
Right. So
Thank you.
Peter and Oleksii, both of our users, have provided these winning solutions. Now I would then first ask Oleksii to present your solution. You have about 15 minutes, and afterwards we have 5 minutes of Q&A.
Okay. So share my screen. Do you see it?
I can see it. I'm not sure if everyone can see it.
I still see the last slide that we were looking at. Oh, okay. Now I see. Thank you.
Okay, so I'm Oleksii. I'm first year master student at the Revolutionize National University of Kyiv, which is located in Ukraine, and I present my solution of this malicious login detection challenge. So a quick review of a data set. It is a data set about events, some of which are malicious, and we need to classify whether or not they are malicious. We have about 700,000 samples, and it is important to point out that we don't have any malicious events in trained data set, so it was logical to apply anomaly detection algorithm. So for the preprocessing, I first applied steps that were outlined in the paper about this data set. I dropped 10 columns, which are specified here, but some of them will return in another way. So then I replaced process ID with a binary variable, indicated whether or not process ID is 0, 1, or 2, which is about whether or not it was spawned by an operating system. I placed the user ID also with a binary variable with about the same context, and bound namespace also with about the same context. Also, I mapped the return value into 3 values based on the common usage of this field. So -1 for bad errors, which is negative values, 0 for just regular success, and 1 for positive, which is successful execution and some signaling to a parent process. Also, then I applied additional steps. I removed occurrences with SAS labels since I'm using an anomaly detection algorithm. Also, I'm applied minimax scaling to the columns which represents number of arguments. And I performed frequency encoding on event ID and thread ID features. So for the algorithm, I chose quantum one-class support vector machine. So first, let's review a classical one-class SVM. We usually apply some nonlinear mapping into a high-dimensional space for the input points. And then we try to fit a hyperplane to separate normal data from outliers. And we can specify the fraction of the outliers by a hyperparameter nu. Also, it is important to note that usually we use a kernel flick so that we do not compute the mapping, but instead we use a similarity matrix between points. So quantum comes into play when we substitute classical nonlinear mapping with quantum feature map and quantum kernel for the classical kernel. So I use the Z feature map, which is a quantum circuit that is parameterized on input data point. I use two layers and linear entanglement, and you can see how it looks for 4 qubits. We apply a Hadamard gates and then a rotation based on the input, 1 qubit rotations, and then 2 qubit rotations as the Z gates. The next step is to compute the kernel matrix. So we first need to develop what is a quantum kernel and how to compute it. I use the so-called compute and compute method, which first we apply a quantum feature map for one point and then inverse of the quantum feature map for another point, and measure probability of obtaining all zero state, which gives us fidelity between these states, and also and in this way similarity. But directly computing quantum kernel for all instances is computationally expensive. So I tried it, and maximally I could achieve 100 samples, and we couldn't train much on 100 samples. So I employed the Nistrom algorithm to approximate a quantum feature map. So instead of having a complexity of number of samples squared, I have complexity of number of samples and number of components squared, and I choose components about 100. So how this works is that, as you can see, we just compute this bottom right matrix, block matrix, Kt2 from carbon 1 matrix, carbon 2 matrix, Ecant 1 matrix, which we compute using quantum circuits, which are simulated or could be run on a real quantum computer. So my results is that I trained on 8,000 samples. For the algorithm, I used stochastic gradient descent. For validation and the parameter fine-tuning, I used 1,000 samples from the test set. And you can see how my solution evolved over time. So first I had 20 components, and I didn't employ thread ID feature and received a score of 0.984. Then I tried more components, increased it to 100, and achieved a score of 991. And then I tried different features. I also tried like first arguments and other features, but what pushed to my final solution is adding thread ID feature, which I received a score of 0.993. So the best result was trained for 31 Apex, and it is interesting that when I trained the classical one classes VM with RBF kernel, I only achieved score of 0.993. Of course, it was much faster, but this is simulation, so it was much slower. But it is interesting, and maybe some quantum advantage could be there. So that's all. Do you have any questions?
Yes. Did you use a quantum hardware?
No, I used the state vector simulator.
And what did you use for building quantum circuits?
I used the Qiskit package.
And when you come back to two slides, no,
Okay.
yeah, this quantum kernel. So when you say you transpose, so these are kind of like randomized circuits. Like, how do you what are the actual gates for this?
Okay, so first we apply, for example, on 4 qubits, we have this circuit. Then we apply basically, we invert the operations.
So P is it a rotation?
P is just
parameterized
rotations.
Okay.
It's rotations about the axis.
And then when you have new 2 times, is it
it is a rotation angle.
Pi minus. Okay. So this value, like 2 times pi minus x 0 times pi minus x1, this is something you devised, right? It just
x0 is the first feature, x1 is the second feature of the input point.
No, but what I mean is to come up with like 2 times pi minus x0 times.
It is a classical map that was presented in Nature paper by IBM, and it is already in Qiskit package, so I just used it.
Okay, got you. And then when you had parameter, like was it n or nu or something? What was that?
Yes, it is represents the fraction of anomalies which so it is an upper bound of the fraction of training errors. So how much outliers do we expect? And I fine-tuned this hyperparameter, so how much outliers we expect in training data.
So even like quantum super vector machine, is this some kind of algorithm that's implemented in Qiskit?
From what I know, it might be, but I just used sklearn library for implementation of the SVM support vector machine, but kernel matrix I estimated using Qiskit library by running quantum simulation of quantum circuits.
Okay, and then this Nystrom. So is it a quantum algorithm or is it an algorithm that's out there and then you implement it in quantum?
So it's a hybrid classical quantum algorithm. We use classical optimization and kind of classical algorithm, but we just use instead of, for example, non-linear mapping that was polynomial, for example, or Gaussian, we instead use mapped into quantum space. So we run quantum circuits, so it's kind of using quantum, but we're training on classical device.
So the Nystrom algorithm, so at what stage is it implemented?
It is implemented before training to. So for the SVM, you need a full kernel matrix of similarities between training data points. But we compute only a fraction of it using quantum simulation. And then the other part we approximate using this Nystrom algorithm. So we have full matrix. And then we use it to train classically support vector machine.
Oh, so this is a hybrid model. So which part is quantum? So quantum kernel is used, but for vector machine, is it still classical? Is what you're saying?
Well, because we use quantum kernel, we can dive into more high-dimensional data. I kind of explain. I don't want to repeat myself, so maybe you can specify a question again.
Okay. Yeah, I think yeah, I think it's a great solution. Um, I don't know, are you gonna write a paper or are you gonna post on GitHub or something?
I can post on GitHub. I'm not gonna, most likely, I'm not gonna write a paper on it. Maybe I will use the same technique for some other research.
Yeah,
So I
yeah.
learned, so I learned
Yeah,
it.
yeah. I was kind of hoping that I could actually understand. But yeah, yeah, but yeah, great. This is great.
You could watch. So basically, I just found this algorithm uh, on Qskit Summer School video. Uh, it's just a Google quantum support vector machine, and it is explained very well.
So is it like the feature map is quantum, and then the kernel is still quantum, right?
It is just a kernel for one. For comparing two values is still quantum. But then the kernel matrix is approximation of quantum because we can compute for some of the values.
Oh,
Because
oh, oh. Oh, okay, okay. Yeah, great. Thank you.
Thank you for those questions and also the answers, Oleksii. Do others have questions? I would have some.
Yanis, could I ask some questions?
Absolutely,
I think
Peter.
my presentation will be short, so but I have some few questions for Oleksii. Like first of all, like so this 4 qubits is just an example, right? It's not your actual implementation.
uh, yeah, it couldn't fit in the
So
slide. So, but it was like
yeah, so how many qubits did you use for this
eight,
problem?
the
Eight.
equal number of features.
Because in the pre-processing steps, I think you mentioned that you used some binary encodings for different I think entries, but I just fear that sometimes because some of the values they are just very small, like they are only consist of like one or zero or minus ones, and the others there goes like 1,000 or like 100,000, and the binary encoding will require more qubits. So do you lose any information or gain any information by the pre-processing step when you do your encoding? I mean that would affect the weights of your features, right?
So yes, I use. So basically, I employ preprocessing that was described in the paper uh, because it is have some like business understanding, let's say, about this. So yes, I lose some information on this step or preprocessing step, but then when I already deploy it in quantum circuit, I don't lose any information. I just deploy these values.
Okay. Yeah, cool. Yeah, I think your approach is really amazing, and it's great to see the solution from SVM. It's just like yeah. Also, maybe it's like more of a comment. Like I really want to see your hardware implementation because I think one issue with quantum SVM with all these kernels is that when you do your gradient descent, there's something happens like it's called a barren plateaus. So like your gradients can kind of does not grow or decrease anymore. So, but that would only happen, I guess, when noise comes in. And I think because you mentioned that you're only doing the state vector simulation, so I guess it does not occur here. And because also we have some simple structures about the data set. So, but yeah, just more of a comment. I would really love to see if you could do this on hardware. Yeah,
Yeah, no, noise can be hard on this, so it was on the ideal simulation.
thank you.
Cool. Yeah, thank you for the questions also, Peter. Oleksii, I think I have basically maybe 2 or 3 questions. So you have on slide 8, you have the runtime that is squared in the number of components, and I think you said somewhere you use about 100 components. And How is this in the classical approach? Like how does this complexity compare to the classical approach's complexity? You use the classical SVM also, you said in the next slide. Do you know?
So it is an instrument approximation also used in classical approaches too. So when you have a lot of data, you just use classical RBF kernel and then approximate it using this algorithm.
Okay. Then I got it. Okay, then just one other question. Like since, well, no, there has been some time since the competition ended. Did you have any further ideas, like when you took some showers, how you could improve it? Like these kind of ideas that just come to your mind at random?
Mm, um, I guess no. Maybe just I kind of learned about that I maybe can stimulate more qubits more efficiently. So maybe I can use more features uh, than I use here.
Right. Okay. No, that's pretty amazing. Thank you so much for this presentation and the very amazing work. I'm not sure, maybe Beck wants to say something. So actually, the only thing I know from Beck is, so while you reached, I think her classical solution was still a bit better than your quantum solution, but like only by 0.001, I guess, right? Yeah. Beck, maybe you
Yeah, it
want to
was
say
very
something about
close.
this.
It was very close. So I was really pleasantly just surprised to find this out. It's like this close there. So who knows? Maybe sometime soon we'll need to start renting some quantum compute for different algorithms that we have to outperform the classical methods. Um, I don't really have as in-depth quantum questions. Uh, but I do wonder about your experience of the challenge. Like, what was the most interesting part of applying this kind of solution to this kind of problem for you?
Well, I guess the most interesting part was to find and learn such an algorithm. So I didn't know about it before, and but I kind of found about anomaly detection that it was using just regular SVM, and then I just searched for quantum SVM and found it.
Very cool. Oh, yeah, I think those are all of my questions. Thank you very much,
And
Oleksii.
also
This
it
was
was
a really
fun
great
racing
presentation.
with Peter.
Yes. Yeah, I'm so glad that you guys could collaborate and chat on it. That's very cool. That's a really cool community forming on the Aqora platform there.
Yeah, amazing. Cool. Yeah. Thank you again, Oleksii, for this presentation and the submission, and also to have you here for the second time already on the second competition that we concluded on Aqora. Right. So now, Peter, the stage will be yours. You will also have roughly 15 minutes.
Okay,
And I
thank
think
you.
Oleksii might have been with the Q&A a bit more than 5 minutes afterwards, but roughly 15 minutes plus 5 minutes Q&A.
Share my screen. I think mine will be very
We can see the
short.
slide and also, yes, now we can
Yeah.
see.
Yeah.
Okay. Okay. Thanks for having me, and thanks for the nice introduction from Beck and Janice. So, I'm Peter. I'm from Cavendish University of Cambridge. I'm first year PhD student, and yeah, a few months ago, I participated in this Aqora challenge with malicious login detection. I think I do not to have to talk about the like kind of the data set anymore because Alex also have a nice introduction. So basically, my solution is very straightforward and simple. It's a hybrid solution as well. So we have the data. Like, can you see my cursor here? So this is yeah, top left corner. So I do the pre-processing of the data set as well as Alexi, and then I do something called PCA, which I will explain later. After encoded the data, then I embed the data with some quantum operations, and this can all be done on classical computation. And then I put them on my quantum computation hardware. So I now use some circuits, quantum circuits to calculate the cluster central distance, which I will show you later. But it's just like I want to separate the evil data set with the successful data set. And then I do this over and over again to obtain the optimum central distance that I could have with my data set. And then because we want to see if the new entries or new data from the base data set is malicious or not. So we input this data set to calculate a new distance, and then we make a prediction. So it's basically a hybrid solution. So how do I do the pre-processing? It's quite straightforward actually, because you can see all the entries on the left here. They are timestamps, they are float or process ID, they are integers. And I just abandon all the string values, which might not be quite useful at this stage. And if you plot the correlation plot, you can see that the evil column or rows are the one we are interested in. And if the correlation is very high, like for example, here it's 0.9, then it means that this data set, for example, user ID, are very useful for your predictions here. So I just selected I just selected those ones with very high correlation values and just get rid of the rest to do some pre-processing, as you can see from this VS Code line here at the bottom. Okay, so after selecting the most relevant parameters, then I do my classical PCA, which is just project the higher dimension object, because now we have 5 or 6 entries, but we need to get it down to 2 dimensions. So I just use PCA to reduce the dimension. And yeah, this is just analogy of how you make the PCA reduction. And then now we have a 2-dimensional data set. So what do we do is that we go on the quantum hardware. So we need to do embeddings first. There are different ways to do it. I think Penina has a very intuitive tutorial on this. So the first one is if you have a discrete data set, then you can just directly use binary encodings. But you will lose some of the kind of informations or your data when the data set is a non-integer, because you will have some decimal places, and this will be a major issue if you come across some like irrational numbers, because you can no longer encode it with just binary values. And then there are some techniques called real continuous dataset encoding. So you can encode your data with rotational gates, and then finally is the amplitude encoding. And then what I did to calculate the distance, the cluster central distance, if you remember from the first slide, is that I implement this circuit. So this is a small breakdown, like kind of a derivation you can find on some of the papers or in the literatures, that if you write down this circuit and you do this kind of like a swap test, then you can find out the distance between your state phi and psi. So that's how I calculate the distance. And it will not use much resource on your quantum computer, because the most, like some people would say that the kind of the most challenging part of the quantum algorithm, or especially in quantum machine learning, is the data preparation step. So I just kind of get rid of the data preparation step on the classical computer and feed the outcome to the quantum computer. And then if you calculate your distance with this sort of strategy, this is kind of the outcome of these 2 different principal components. Remember, it's 2 dimension because I've reduced this with PCA. I don't remember exactly which blue or the yellow ones corresponds to the evil data set, but it has to be one of them. And as you can see, there's a clear boundary between these 2 data sets. There is 2 different types of data set. And then the red cross is just the centroid that we need after the optimizations, after a round of optimizations. So if I have a new data set come in, and for example, this corresponds to the points in the circuits, and then we compare this to the center, which is one of the crosses here, and we calculate the distance. If it's closer to the successful data set, then we say it's not malicious. If it's close to the evil data set, then we say it's malicious. And then the centroid 1 and 2 just stand for the 2 different types of data set I just mentioned. And for the last couple of days, I think to get over Oleksii's score, I just kind of play around with the centroid 1 and 2, just change them and to do some optimizations. And at the very end, I think I got pretty satisfying score. So yeah, like 0.993, and this is a kind of piece of my main solution code here, and yeah, that's all I've done for this challenge. Thank you.
Thank you, Peter. I'll maybe then start with the first question. So you said on the slide before that it was a fierce competition between the two of you. Like every day, there was I recall the scores getting up. That was very, very cool. So you said that you tweaked them until you could get the. I think it was in the end the same score as Oleksii. Do you think there can be further tweaks that you can?
Yes, I guess so, because I did this challenges quite some time ago. So I kind of I just leave the challenge alone, because I think well, no one else is gonna challenge me, because like I don't see anyone else. But then a few days ago, and Alex comes up, so I kind of just tweaked this a little bit, and it comes up. But I'm not sure I haven't calculated the upper bound for this kind of solutions. But I guess there might be, but it will be tricky, because as you can see the data set, there's actually some overlapping points in the projection. So it might just be that I reached the very end, and then yeah, there's no way to optimize it. But I don't know yet. Yeah.
Yeah, right. And I hope I say the right thing, but as you're saying, like there is this overlap, but could you take another dimension and maybe separate further by this?
Yes, I think that would be a very good proposal, but it will add a little bit more complication to the quantum part. But that would be possible. Like you project on a higher bit, maybe 3 or 4 dimensions, and then do the quantum circuit implementation. Yes, thank you.
Yeah, right. And how many qubits did you use now?
I just use I think I don't quite remember. It's 4, 5 qubits. It's very small. Yeah.
Okay, I see. And you were running also on a local simulator, not on a.
Yeah. No, only a
Okay.
local thing.
Okay. Other questions? I see also Jamie joined us. Jamie or Sam, do you have any questions?
I have a question. So as I understood, you somehow load all points at once in the state.
Yeah. So it's very much the same thing as you did with pre-processing part. So I kind of how do I go back? Yeah. So I just load them at once, and then because I did PCA, so kind of it with classical solutions, it only gives me a two-dimensional data set. So that's kind of you don't need to care about all the other parts of the data set. And you have just very few entries. And you can load these on your quantum circuits.
My question is, how do you load the entire data set in one quantum state? Or you are not doing this?
You mean entire data? No, I'm not doing that step. That one is I didn't do that. It just load all the entries at once, not all the data set at once. So each one of them corresponds. Yeah, each one of them corresponds to one sample, and then I do the circuit input optimization with each of the samples. But yeah, I did not load them all at once.
So it wasn't like an embedding per feature, it was an embedding for the whole like row of features?
Yeah.
Okay. That's very cool.
Okay.
Also really like the cat embedding drawing on whatever slide that was.
That one was
Excellent.
a screenshot from the Penina implementation. Yeah, I really liked it.
It's great.
Cool. Thank you. Are there more questions? Sophie, do you have any?
Yeah. So after you do PCA, Oleksii used min-max scaling. So when the values are like, very one is like in the thousands and one is like, 0 point whatever. Yeah. How did you scale?
That's a very good question. But I think one of the advantage with this sort of technique, classical implementation, is that you don't need to care much about the scale because, um, like for example, here, for the if the value for thread ID is very high, I don't need to care about it because I only when I do PCA, I only need to care about the kind of the variance or the mean value of this data entry, and it get just automatically mapped to your two-dimensional space. And then but you might need some truncations there, but that would be after your processing step. So I guess that would be less.
Oh,
Yeah.
oh, oh, yeah. Yeah, I guess I kind of didn't really understand the process, but this looks really so like per entry. Oh, so per sample, you're selecting
Yeah.
only the highest two features by
Yes,
this
it could be
method.
highest. Yeah. But the highest
Like so
few, but
like
not.
yeah, so like per sample, it could be event ID and args that are contributing the most, and then you
Yeah.
pick
Yeah.
that. Oh, wow. Wow, amazing. So once you do this, like, do centers move? Like,
Yeah, it will move. So you have to kind of do the optimizations there with your circuit. And yeah, that's what basically I was playing around for the last few days. And then you can get you have to go back to see if this is the best kind of best centers you have, and then compare it to your new data entry, and then recalculate the distance to do it over again.
so you're kind of doing one at a time. So,
Yeah.
oh, got you.
Cool. Then, yeah, thank you again, Peter,
Thank you.
for your presentation and your submission. Also very cool. And yeah, just for everyone again, like both of you had the same score at the end, a score of 0.993. I think where one would have been a theoretical maximum, which I'm not sure if it's like feasible to get. And then let me share my screen again. I hope it will basically work from where we stopped. This looks good, yeah? Oops, let me see. All right, yeah. So thank you again for your presentations, your submissions to this competition on malicious login detections by Novacene. And as I was just saying, so both of you had the same score. So we were wondering if there should be one winner or not, because Oleksii had like the solution one day before Peter. But in the end, we decided, or it was more up to Novacene, decided that both of you will be awarded the first prize in this case, which I think is also very fair. So congratulations. You will receive this badge on your Aqora profiles. There's also the opportunity for further collaboration, I believe. Maybe Beck will say a few more words or reach out to you afterwards. We can also together like kind of write a write-up so that this is accessible also to the public, because I think it's like great solutions, and understanding how quantum computing can be applied to even small scale but real world problems is very, very important and amazing to see. Beck, do you want to say some more words?
Yeah, we're going to be writing a blog post about the experience. So we'll be sharing that once we have some drafts ready, and it can be shared on LinkedIn and wider, but also on our home website of novacene.ai. Yeah, if there are future hackathons, we're going to be happy to participate again, of course, and try and provide interesting challenges like this. We hope we can stay in touch. Thank you both again for such really cool work. And it was really great to hear your explanations and see the like very creative and very different approaches that you took to solving the problem.
Thank you very much, Vic, for the nice words, and thank Yannis for hosting everything. Thank you.
Yeah, thank you for the competition. It was very interesting.
Mhm.
Of course. You're welcome. All right, then let me conclude this by just saying a few more words. So I think we could have added one more slide just to show what's currently on the platform. No, we don't have it. Like there's a few more competitions right now that you might want to check out. Like you on the call, but also others potentially watching this. We have a current hackathon with CERN. On high energy physics with 2 competitions running until the 28th of March. So I think at least I've seen Peter joining this event. So that will be might be worth checking out. And then also we have this current competition with APRI on the how is it exactly called? Let me see, the Quantum Challenge Fusion Energy. Or the Fusion Quantum Challenge. This is the right wording, where we're not looking, or they're not looking for like a code submission to rank on a specific metric, but rather project proposals. So, and there's a big prize pool attached to this. The first prize can win $10,000 even. So also this one you might want to check out. And there will be more coming. Last but not least, I think we just extended also this one for Q&As for stock price trend predictions, which could also be interesting. And I think also there, at least Peter, I've seen you. I'm not sure if I've seen Oleksii yet, but might be there. This is going for until the end of the month. Right. And then just some last word advertisements. We had released it when we had our last presentation with Engine, actually, this quantum algorithms as a service, or we call it Q3S. So if you're exploring quantum computing, this should provide you with some easy way to get into it, supposedly. We host some variational algorithms like QAOA, VQE, provide some visualizations, and then you can use this to either work on your solutions on Aqora or also outside on other projects, just to give this small advertisement here. But with that being said, yeah, just once again, Peter, Oleksii, and also Beck, like, thank you all for this great competition with these amazing outcomes. It's really great to see, I mean, these smart people like you, Oleksii from Kiev, Peter from Cambridge, just like spread around the world. And I think this is what we do Aqora for, and how we hope that we can have an impact in this technology evolving.
Thank you very much, Dennis.
Thank you.
Cool. And then have a great day, everyone. And see you in the next competition, I hope.
Yeah. Thank you.
Thank
See
you
you.
again.